All right, we are going to look at an extension of the ratio test with one example before we get to the very last topic of the year. So here we go. And the extension basically adds absolute value bars to the ratio test. There's a couple reasons that we would want to do this. It's the same ratio test we saw before with the addition of the absolute values. And you might look at that and say, well, what do we need those for? Because the ratio test says we have positive terms. And while that's true, by adding the absolute value bars, we allow this test to be used to check for the absolute convergence now of an alternating series. In addition, it allows us to solve a problem like this down here. Here's a new series. Doesn't look so, well, it looks a little bit bad. We'll take a look at it. 2 to the n plus 1 times x to the n divided by n squared plus 1, and the sum from 1 to infinity. But what's different about this series than others that we've seen is there's a variable in there. And so the question now becomes, for what values of x will this series converge? And that's a different twist on the ratio test question. So by adding in the absolute value bars now, we're going to include x's that would lead us to convergent alternating series. So if x were negative, then we're going to get a negative to the n power, and it's going to flip back and forth and become an alternating series. So let's take a look at this problem and attempt to solve it. So here we go. Got the ratio test in the corner in case we need to refer back to it. But here's the way this works. We're just going to start with our ratio test. And the ratio test says that we're going to basically take this thing, but with n plus 1. So that'll look like this. 2 to the n plus 1, x to the n plus 1, and all of that divided by n plus 1 squared plus 1. This will all be divided by the original term. That's 2 to the n plus 1, x to the n, and all of that divided by n squared plus 1. Difference this time, everything sits at an absolute value, and we are looking at the limit as n approaches infinity of all of this. And what is the deal here? Well, now we're solving for x. When will this converge? When does this limit, here it is, when does this limit converge? It converges when it is less than 1. So this is what we're trying to solve. And it looks pretty horrible, but it's going to break down the same way the ratio test broke down before. What I'm going to do, just to save a little space, is get rid of all of this, do a little simplification right here, because we know the first step is going to be to take this denominator and flip it to multiply. So I'm just going to rewrite the entire term and flip it. So now our absolute value sits up here with this term now being flipped around. Okay. Next thing I'm going to do is I'm going to put some things together so it might be easier to see what happens in this limit. So we're looking at the limit as n approaches infinity, and it is a big absolute value. We've got our 2 to the n plus 1 divided by, I'm going to move this 2 to the n plus 1 directly underneath it, times. We've got an n squared plus 1 that was in the numerator, here it is, divided by our n plus 1 squared plus 1, and finally, x to the n plus 1, that was here, divided by x to the n. So I've just put together the pieces that are going to make this a little bit easier to compare. So here we go. In the first piece, we're going to really be looking at 3 separate parts here. 2 to the n plus 1, we know what that is. That's 2 to the n times 2 to the 1, or just 2, and then plus a 1, divided by 2 to the n plus 1, times n squared plus 1 divided by, if we multiplied this out, n squared plus 2n plus 1, so plus 2. And finally, this is x to the n times x to the first, divided by x to the n. I get my x to the n's canceling, so that's going to leave us with just an absolute value of x. This middle portion, in a limit as n approaches infinity, highest degree over highest degree, this is a 1. Everything's positive, so it's out of the absolute values. Here's my absolute value of x. And the only thing left to figure out is what's going on over here. Well, if I take this 2 and factor it out, I get a 2 to the n plus 1/2 divided by a 2 to the n plus 1. And in the same way that highest degree over highest degree is all that matters, in this case, I've got an exponential plus a half, same exact exponential, 2 to the n, 2 to the other same, plus 1. Certainly when n is very small, the half and the 1 mean something, but when n is 10 or 100 or 1,000, this becomes so unbelievably huge. These don't matter. This is very similar to the highest degree over highest degree. So this piece of it is 1. But there's a 2 out here as well. So where are we now? We're at the limit as n approaches infinity. This first piece turns into this, which turns into 2 times 1 times this 1 here times this absolute value of x. And this is supposed to be less than 1. So that gets me an absolute value of x less than 1/2. And this occurs when x is between negative half and positive half. That's when the absolute value of x will be less than the half. And this could be the solution to this problem. So as long as x stays between negative half and positive half, this series will converge. And that is definitely an extension on what we had looked at for the ratio test. I'm going to post 2 practice problems that are kind of like these for you to take a look at. And we're just going to wrap the week up with this last set of problems on ratio test. Next week, we'll take a look at the very last topic and then get started on review. Thanks for sticking with it, everybody.